All right, well, first of all, you should all thank Danny because he bought the food tonight. And I have to say, I've done these.
John can tell you, we get better food here than they get.
Yes. Yes, I've done these presentations all over the country, including Washington, D.C., New York, and your food's the best. And so now a word from our sponsor. This is not about cameras as much as it is about Hitachi, the global company. Hitachi is a big company, but the important takeaway here is we spend more money on R&D than anybody in our business. Now that's aggregate for all of Hitachi, but still $4 billion is a fair amount of money. And we have more world patents than any company. And so Hitachi has about 350 divisions. These are some. Certainly you've seen belt sanders at Lowe's. Those are actually not made by.
Truck.
Yeah, you want that truck. The belt sanders and things like that at Lowe's are actually not made by Hitachi. Hitachi has a commercial division that makes much more expensive tools. But anyway, you get some idea. We have an energy systems company. This machine in the lower left is proton beam. It's for cancer treatment. It's marketed under CyberKnife. Helio Castronova's won the Indy 500 with Hitachi engine management. We make fuel injection for Chevrolet and other people. And the data centers, you all probably know Hitachi Enterprise hard drives. That was sold off. Then Hitachi servers were very high performance. That was sold off. Hitachi Vantara now is mostly consulting and software. We supply live LFM, live facial matching to Homeland Security. So when you go through the Atlanta airport, you're being watched by Hitachi cameras and matched on Hitachi software. And this is all border security here. These cameras are mounted on lifts that can see, 5-10 miles in the distance with filters for clouds and fog and stuff like that. We developed the Satacon and patented it a long time ago. At this last NAB, we won an Emmy for the MOS single chip sensor in cameras. We have 4 divisions. Obviously, I'm broadcast and professional. Industrial video systems, does machine vision, surveillance, stuff like that. You've never heard of Crucial Imaging because that's all OEM. It's Hitachi equipment, but you never see the Hitachi name. And we bought Comark TV transmitters and encoders. This is our newest camera. It was the best of show at the last NAB. It's called the 1800. I'll tell you more about it later. We developed the first 4K camera with 2/3 inch sensors. This is our 8K camera. This was the 5th generation camera. We're on to the 6th generation. I'll show you that later. But this was a single imager. The latest one is 3 2/3 inch imagers. Parallax is the name of the transmitters that Comark makes. They won Best of Show for their new UHF low power transmitter. Okay, so that's a word from our sponsor. I have assembled presentations on HDR, ST2110, my post-NAB wrap-up that I did about a week ago at SMPTE, and I managed to edit it down to just 172 slides. So here we go. Oh, you were paying attention. It's not 172 slides. So once upon a time, everything was simple. It was NTSC. We liked that. You knew what was on that connector. Not anymore. So as the title of this presentation is, it's a hybrid world. We have a lot going on in cameras that isn't real obvious. The transition is now, well, okay, the transition is from CCD to CMOS. That's pretty well done. Now the transition is from CMOS rolling shutter, which they all started as, to global shutters today, and there's good reasons for that. HDR is wonderful, but difficult to manage in workflow. I'll talk about that. We've got all kinds of resolutions that all need to be merged. And then we have SDI versus, notice the term versus ST2110. They are in competition with each other in effect. And there are cases where one is better than the other. This is the camera. This is a listing of the things that the top cameras from all the manufacturers, it could be Sony or Grass Valley, Ikegami, we all do all these things in our top camera. I'll let you look at that for a second. I'm not going to read the slides if you haven't figured that out by now. So you need to keep up. The virtual control is, we use dashboard. All our competitors have a type of GUI, user interface, for remote control of the cameras. It varies somewhat by how they're implementing it. We use ROS Dashboard, which is a logical way to do it, and it's a very nice looking user interface. So these are the trends that I saw at the NAB. Now I'll let you look at that for a second. I think one of the biggest ones is HDR is accepted in that we all agree this is a better picture, but how do we use it? And I'll talk about that. Also, the 4K buzz has sort of leveled out now, and people with 4K cameras generally are shooting 1080 60p for archive. I'll show you in a minute the bandwidth costs. Bits are bucks. So there's the problem with that. This is the agenda of the things I'm going to talk about. I don't want to give you a sip of water from a fire hose. Very often a presenter wants to tell you everything he knows. Lucky for you, there isn't time for me to do that, so I'm going to go fast, and you have to stick with me the best you can. So let's talk about where we came from with imagers. You probably know, because I see a lot of gray hairs in here like me, that the CCD started out as a delay line used in time-based correctors back in the day. And it has the property of being able to store and shift or store and move a bit of data. And then someone discovered that it was sensitive to light, and the CCD imager began at that point. CCDs were generally global shutter. There was a FT, not very good. There was an IT, better, and FIT, and they all worked a little bit differently. But CCDs were generally considered global shutter. A CCD is an analog device, and MOS and CMOS are digital devices, so it's a little hard to compare them, but you get the idea. So MOS and CMOS sensors are what is used today virtually everywhere now. We still have CCD cameras, but our CCD stock is limited, and so is everybody else's. And I'll tell you why in a second. So the global shutter basically opens the shutter, acquires the entire frame at one time, and then closes the shutter. A rolling shutter is sequential. It's almost like scanning. And the problem with that is things happen between the beginning and the end of the scan. The real problem for CCDs is they're expensive, they're analog. They require a lot of external processing equipment to take it from analog to digital. They have great properties, but it's not easy to get them to be a camera sensor. CMOS and MOS, obviously related, are much less expensive to build, and that is the primary thing that is driving it. Oh, by the way, when you make a global shutter CMOS, the cost is back up again, but it's still not as expensive as a CCD. So why do we need global shutter in the first place? I think you all know about LED walls. There's a pulse width modulation and refresh rates that cause havoc to a camera. Our eyes and brain are very forgiving, persistence of vision, and a whole bunch of other things We never see it, but the camera sure does. And so that's the problem. And it's all about the relative frequency of the display and the camera. So you've all seen this banding. You've all seen this. And just to show that it's really the LED, it's not a large screen video wall that's the problem, it's the LED itself. The problem exists with lighting just the same. So the other thing that is a bit of an issue is moire. It's always been an issue, clear back, probably maybe even the tubes, but certainly with solid state imagers, when you get into high resolution, sharpness, a lot of aperture and image enhancement, a striped shirt starts buzzing at certain zoom ranges. We have the same problem today with an LED video wall. So you can filter in front of the camera lens or at the camera. You can filter at the display, both of which reduce sharpness. My opinion is you open the iris, which shortens the depth of field, and you will put the background, the wall, out of focus slightly, and it only takes a touch. You can't even see the difference in sharpness, but it gets rid of the moire. The other problem you have with rolling shutter is things bend. You know, I think that's a rubber hose golf club there. No, actually, that's just rolling shutter. And this is what has happened from the beginning of the scan to the end of the scan. Okay, let's talk about displays. They say retention is better when you go fast, and I force you to keep your attention focused. So I'm going fast. High-res LED displays are down to 0.9 millimeter pixel pitch. That's the triad of the LEDs, which is pretty amazing. You can stand right next to, well, it looks like a TV set. You can stand right in front of it like these people, and it still looks good. These are obviously indoor displays, but they really have come a long way, and they're using these micro LED blocks so that they can build 8K displays like this one. 33 million pixel triads on that display. In terms of professional monitors, the Flanders Scientific is the best one I've ever seen. It happened to win the NAB Show Product of the Year. It's made by a Chinese company under agreement with Flanders. It is amazing. It's 3,000 nits. That's a center area. You know, when someone specs nits brightness on a monitor, they're not talking about the whole raster, right? Or the whole display. They're talking about a small area. I think it's called like L2 or something. It defines a small area. But the point is, HDR brightness is needed at the peaks. So it's fine, it doesn't matter. They had a fireplace, logs with flames burning. I've never seen anything that looked so realistic because it had the brightness that you would expect from fire. It also had the ability with wide color gamut to display the depth of color at that high brightness, because that's another trick that people don't always understand. So this was a fantastic monitor. Now let me talk about my favorite subject, the idiots on the consumer side. There is no bottom to what the consumer marketing people will do. First of all, as displays get larger, the fabs have to get larger. The fabs are those companies mostly in China and Korea that are building fab panel. It's 8 feet by 16 feet as it comes out of the fab, and then it's cut up to be your TV display. They keep building bigger and bigger fabs because we want bigger and bigger TVs. And the importance is that they get maximum usability of the fab. So that's one of the things that's going on right now. and then of course the pixel count. So not only do the fabs have to be bigger, but they have to be higher density pixels. And in some respects, they're their own worst enemy because they always need the next big thing. Just about the time that 4K and in most cases HDR is being widely accepted, the price has eroded and they need to jump on something new to crank the price back up again. And that's what's going on. Now, consumer marketing purposely confuses buyers because a confused buyer is a good buyer if you're a consumer company. And so one of the things that Samsung has done is named their quantum dot LED TV QLED. Very confusing for the average consumer versus OLED. In addition to that, the terminology is wrong because LED TVs are not LED, they're LCD. They just use LEDs for the backlight. They might be zone, they might be full array, they might be edge lit, but that's all the LED is doing. But LED sounds cooler. So that's why they do that. Now, as you know, there are true LED displays, the micro LEDs and the big screens, but that's not consumer TVs. Okay, I've said enough about the consumers. I'll get off my soapbox about them. Size matters. On the consumer side, the TVs keep getting bigger and there's no end in sight. 75-inch and bigger is now the new standard. So if you've got a 65, get rid of that piece of junk and run out and buy an 8K 75-inch. But the market is expected to grow significantly. And I have a friend who's out looking at buying a new TV and he's in the 75 to 80-inch range. Part of that is if you have that kind of resolution, you need a really big display to see it. And I'll get into the viewing distance issue that we have. But at this point, a 98-inch 8K is kind of expensive, but you get the floor stand. So, hey, there you go. It's worth it. It's absolutely worth it. Samsung has not announced a price on their 90-inch 8K. This 165-inch LED TV has been discontinued, but the price goes up exponentially as the size gets larger. It's not linear at all. The Sony 98 8K is 70,000, but I think it's about 78 or 80 inches 8K, and it's 25,000. So the price is highly nonlinear. This was Sony's 25-inch diagonal. I snapped this picture at the NAB, 25-inch diagonal micro LED. Anybody notice anything at all that's a little funny about this picture? You see the rabbit ears? Yeah, I don't know who that was. I mean, I walked up behind there. I never noticed it at the time, but somebody's got rabbit ears. And I'm not talking about TV antennas. No, I'm talking about bunny ears. Samsung has put in a micro LED screen in Los Angeles, multi-million-dollar in a theater. And Samsung is pushing this kind of display for movie theaters. And I'll get into nits brightness and all those issues in a minute. Okay.
You didn't say inch, you mean feet.
Oh, I'm sorry. 25-foot diagonal, yes. Thank you. That's a big difference. Yeah. And thanks for paying attention. Okay. So high dynamic range. This is my favorite subject. I've been doing this kind of presentation for about 2.5 years. It's important that we all get on the same page with what HDR is not. So I'll let you look down. The one that I get the question all the time is, oh, isn't that the same thing as HDR on my iPhone? No, you're taking a single still. We're doing 60 per second. You can't do it in the same way of combining multiple exposures. Although there is some nutcase company in Hollywood that's actually trying to do it that way. It takes like a supercomputer to keep up with it because you're assembling 3 exposures and making one HDR picture. I don't think it will fly, but they're trying to do it. So those are the common misconceptions, just so we're all on the same page. This is a simulated image of HDR off or SDR and HDR on. What you notice is there's no detail in the sky. The picture on the right has a significantly different feeling than the one on the left. You'll also notice more sharpness in the building. That comes with contrast. That's just free. There's no attempt to actually sharpen it. Contrast gives you more sharpness. You also notice more detail on the street, especially under the tree, and look at the blue parking sign. The color kind of jumps out on that compared with the other one. Okay, now we're talking about the same thing. Oh yeah, I'm sorry, thanks for noticing. The antenna, it's gone, it's blown out, just disappeared, clipped. I'm going fast, so I'm missing some things, and thank you again. Why HDR is better than 4K? We sit too far away from our TVs. In 1980, Bernie Lecter, who worked for RCA, determined the average viewing distance in the US was 9 feet. Interestingly, worldwide, it's 3 meters. So there's some reason that people sit at that distance from their TV. Keep in mind, in 1980, we were looking at 24-inch TVs. And now we're looking at 65 and 75. But we still sit the same distance from the display. Odd. Point being, you can't see 4K at 9 feet on a 65-inch TV. That's the point I'm making. 105-inch, Samsung had one for $130,000. It's discontinued, what a surprise. It might be cheaper to sit closer, but we never have, and I don't think we ever will. I think that's why the displays are getting bigger and bigger. I mentioned bandwidth earlier. This is the problem with 4K on our side, not on the consumer side, but for us, bits are bucks. Whether you're storing it, editing it, transmitting it, it costs money when you have a lot of bits, and that's 4K. Now look at HDR. So there's a very small increase in the total cost for bandwidth when you go with HDR. So it's bang for the buck that we're talking about with HDR. The other thing is you can't see 4K from the average viewing distance. You can't see the full resolution of 4K at the average viewing distance, but you can absolutely see the improvement in HDR. A short digression, I did PBS TechCon a year ago. We had a, 25, 30-inch Sony OLED HDR monitor. The room was huge. You know how those rooms are in Las Vegas. Everybody in the room could see it when we switched it from SDR to HDR. That's the point. So how is it that we're stuck with BT 709? How did that happen? 85 years ago or something, somebody established a standard based on the CRT. The CRT couldn't get any brighter than 100 nits. And it also took a lot to get the CRT moving, so we had a curve that was inherent in 1886, the standard, that we had to compensate for in the cameras. Okay, who knows what that is? What TV that is? Anybody? No, that model TV. One guy got this, James Snyder of Library of Congress in DC. Figures, you know. It's a 1939 Dumont, 14-inch black and white. That's our standard that we use today for dynamic range. Isn't that pathetic when you think about it? Now, there is this little problem of about 1.4 billion TVs in the world, and so it's a little difficult to make a wholesale change quickly. But I'll get to that in a second. Let's talk about brightness, because that is, after all, what HDR is about. And HDR is more about the display than it is the camera. Our cameras have been, everybody's cameras have been able to do more than 100 nits for a long time. But there was not a display that you could count on that would display it properly. So a theater is 50 nits, actually 48 nits. That's ridiculous, but the environment is completely controlled and it's very dark. And you sit where they want you to sit. And you're not way off axis, in other words. And so they can get away with it. Standard TV is 100 nits, that's BT 709. Hybrid log gamma and PQ are between 1,000 and 2,000 currently. Dolby suggests 10,000 nits would be nice. That will hurt. Some people call that visual loudness. I really don't know. But if you look at a car and the sun glints off the windshield, that hurts.
Sony showed at CES a year ago their display, which they claimed was 10,000 nits. It was painful. You literally needed sunglasses.
Yeah.
They had a shot from the remake of Annie where the helicopter flies with the sun in the background. And when the sun came up, it was like.
Yeah. Joe Bogatz from Canon had a monitor like that last year, not this one, 18. And he said, okay, I'm going to run this clip, look away. Okay, and then you can come back and look at it. Yeah, that's the kind of brightness we're talking about. So the other problem is, and this is what is preventing broadcasters from doing it, is ATSC is based on 8 bits. So that's the end of HDR for broadcasters until they get to ATSC 3.0. You have to have 10 bits, otherwise you get this terrible banding and quantization errors. I want you to know that resolution, high dynamic range, and wide color gamut are all 3 separate things that are not related. So you can have any resolution with HDR, with and without wide color gamut. But I'm going to talk about color gamut because it's an important thing. One of the lying consumer marketing things is we do wide color gamut. By that, Sony actually says we do 20/20. Wide color gamut in their consumer TVs. They don't. They can't. Nobody can do it. Just like 10,000 nits brightness, what they're actually doing is DCI P3, which is more. That is the black triangle. But you can see where 20/20 is. It's way out there. You really need lasers to get to that color. And so we can't really do all of wide color gamut, but we can do a lot. And it's really spectacular when you have things like brass and gold, because traditionally when you additive color, you end up with white and no color. So how can you get lots of color and lots of brightness? More color volume and more brightness. That's how it works. So some of the HDRs have metadata to help tell the TV what it is. This is assuming you have an HDR TV. And you can see the visual difference between those. Every 4K TV that says they do HDR does HDR10, no exception. HDR10 is PQ. And this is an example of that. Many of them do more. I'll show you a chart in a second showing the confusion on the consumer side and which versions of HDR they do. So hybrid log gamma has no metadata. It's intended to be live. It was developed by BBC and NHK, who are broadcasters. That's what Hitachi supports. Because it has no metadata and because it is a hybrid curve, like the name implies, hybrid log gamma, we have a great deal of compatibility with modern standard dynamic range displays, not CRTs. But a 5-6-year-old flat panel can display a whole heck of a lot more than we've allowed them to do. And that's what hybrid log gamma does. And it's unlikely that there will only be one HDR curve. PQ and Dolby Vision are used in post-production by movies and things like that, where they spend a lot of time with color and tone grading and artistic stuff, and they metadata, and that's not what, well, it's not what Hitachi has been talking about. We're talking about live broadcast HDR. This is the most important slide of the whole deck, in my opinion. This shows the three curves. Red is SDR, blue is log gamma, hybrid log gamma, and green is Dolby. Dolby PQ and Dolby Vision are the same curve, okay? But Dolby Vision uses 12 bits and more metadata, but the curve is the same. So this is what it looks like when you have a precision 4K HDR monitor on the left and an average HD SDR monitor on the right, feeding it hybrid log gamma. The question is, could you stand to watch either one of these? I say yes. Okay, now let's take a look at the Dolby PQ curve. The curve starts faster to stretch the blacks because we want more detail in the dark areas, and it tails off quicker because it's going out further on the brightness range. So what do you think is going to happen when we do the same two monitors, only this time we're feeding it PQ? Just what you would expect. You have no blacks because black goes up fast, and you have no whites because on a normal display, it never even gets close to full brightness. That's the problem. This is the confusion on the consumer side of HDR profiles. Isn't this great? And you know what I like best of all is, does it have a pointer in it?
Yes.
Oh, okay, let's see.
Very top or bottom.
Maybe this one? Uh-oh. Uh-oh, okay. This one. Is this? I saw it, okay. Let me know if I hit you in the eye, Lisa. Okay. Oh, it's not. Well, okay, Samsung HDR10. See, HDR10 Plus. This is Samsung's way of getting around paying Dolby royalties. It is the same thing as Dolby Vision. Samsung and Panasonic got together and said, we don't want to pay Dolby. Dolby says it's $1 per TV, but how many million TVs? So they came up with their own, and as you can see, Samsung, Philips, and Panasonic, I guess Amazon is in on that. But generally speaking, you see the biggest circle is HDR10. That's PQ. Everybody does that. LG is one that does a lot of different profiles. They don't seem to have an axe to grind like some of the other manufacturers. So I told you I would talk about workflow because I think we all agree HDR is a good idea, but how do we use it? And these are the different subjects as it relates to workflow. So the first thing you have to do is get everything the same. So if you want to do a production, you have to convert any SDR to HDR. That's assuming that the switcher is HDR and the ultimate output is HDR. So those three things need to be converted. Then you have the production switcher, which is HDR. It goes to a DA and outputs HDR and then goes through a conversion to SDR, and that's the way you do it. It's not the end of the world, but it is some conversions and some processes. These are all the things that are different between SDR and HDR. So when you convert, you've got to deal with all of these. Some are more difficult than others. So what we do, and what the other camera manufacturers are probably doing as well, is our CCU outputs HDR and SDR. So that solves that problem. But what really is more important is we use a technique called inverse gamma. Rather than a lookup table, which is just a mathematical estimation of what it is and what it should be, we know what the HDR curve is. We put it in there. So we take that out with an exact inverse curve. That gives us flat, linear, raw, whatever you want to call it. And then we put the SDR curve in. And what we end up with is an HDR that's as good as HDR can be, and an SDR, which is exactly the same as an SDR camera, which after all, that's the whole point. So how does this work for shaders in mobile trucks and in live situations? Very simple, you shade for SDR. Since SDR lies within HDR, if you're shading for SDR, you're not going to have a problem. Once you set the offset, about 9 dB gain difference, Once you set that offset, you can just work it as SDR and don't worry about the HDR. It'll take care of itself. This is a simplified delivery where you have the inverse gamma mapping in the CCU. It goes to a mobile truck, for example. There's an SDR feed that goes out. The HDR feed goes to master control, network control, whatever. And they may use a 3D LUT at that point because you can't do the inverse gamma at that point because you don't know exactly what it was when it started in the CCU. And they'll use a lookup table to create the SDR feed. Using a lookup table will give you very close to SDR. It will not be exactly the same as a native SDR camera. And the other way, this was done for the BBC Royal Wedding. You have two you have two switchers. One is slaved, and you can see there's every version of the outputs that you would need for a world feed. Yeah, yeah. Well, remember what I said is going to be a hybrid world? Now, this is an example. The other great thing that has happened is ATSC 3.0, Technicolor did a wonderful job, in my opinion, of putting together the A341 standard for ATSC 3.0, single layer HDR1. It basically encodes the difference between SDR and HDR in metadata. It's then transmitted, received by the TV. If the TV is an old SDR, it doesn't know any better, it gets SDR. If it's an HDR, it detects the signal and adds the metadata, the additional information, automatically to make it an HDR picture. It's a great problem solver. And I believe that this is the solution. Of course, we have to get to ATSC 3.0, and that's another story that I'm not going to talk about. 8K, everybody has heard about 8K. It's all the buzz these days. At the NAB, there was a lot of talk about it. One of the interesting things, I did a demo of our 8K for a major sports league, which wanted to cover the entire field, and then no matter what happened on the field, they could cut it out, zoom in, and replay it. This is for officials. Of course, it would work for consumers as well. Panasonic has done a very nice job of doing the same kind of thing, 8K camera, for different cutouts with tracking. As these people move around, there's a little sensor on their arm, and the cutout moves around and follows them quite nicely. Much better than I would have thought. It's all digital, of course, but you have a raster that's 16 times larger than 1080 60p. So you can cut it back a lot. You know, those cutouts there might be HD. Maybe number one is larger than HD. But the point is, you still have a lot to deal with. This is our new killer camera. It's 240 gigabits per second. 4 times slow-mo. 3 chip, 2/3 inch, uses standard sports lenses. Obviously, we built this for NHK and the Tokyo Olympics. It's a monster, and it has a monster price to match. So what you want to do then is put a monster lens on a monster camera. So between these two, you'd be talking about $1 million or so, you know.
I got a question.
Yes.
Is there a cinema equivalent for 8K in terms of the aspect ratio? You know, it's like UHD.
Yeah, yeah.
HD,
Where we have the
6.9.
cinema version.
Right. Is there anything in the works for that?
As far as I know, 8K is 8K. There is no difference between cinema and broadcast. There is only one raster size.
Unlike 4K.
Unlike 4K. Yes, right. Yeah.
Yeah, you said a standard sports lens. What was the mount? What do you mean by standard?
Oh, B4 mount. Yeah, a standard B4.
Oh, so it was a 2/3 inch. It's a 2/3 inch camera.
That's 3 2/3 inch
Okay.
imagers. So it uses a standard broadcast B4 mount. You can take any old Coke bottle lens that you have left over and stick it on there. Not sure you get 8K out of it. But yeah, that's the whole idea. For the Olympics, you need a big lens. And this is a massive 7.5 to 1 zoom. Wow. Yes.
I think he's talking about cinema, but remember, for cinema, not counting whatever IMAX does, the core aspect ratio there is 185 instead of 177. So you do have a difference there.
I suppose that when 8K video gets to theaters like that Samsung micro LED theater in Los Angeles, we may have some issues. Yeah. That's a fair point. I don't know that. And let me also say, Hitachi doesn't build cinema cameras. We don't build ENG cameras. So to some extent, I'm isolated from that discussion. We build cameras for broadcast and live. So, but that's a good point, fair point. Okay, last subject. How am I doing? Okay. SMPTE ST2110. Also known as VoIP, which I can't stand because to me, VoIP is video. I mean, voice, not video, but it sounds better than MOIP, which would be media over IP. To many people, especially the mobile companies, there's nothing wrong with SDI. It's a small contained facility, and 12G SDI works very well for them. NEP, Game Creek, and a couple other mobile providers wrote an open letter to the industry saying, just give us 12G. We're fine with that. We don't have long runs. It's all inside the truck, and 12G works. I'll get into the details on ST2110 in a little bit. But the other thing is, SDI has been around a very long time. Look when the BNC connector was patented. And by the way, does anybody know what BNC stands for?
Internet and compact.
No?
British naval.
It's two guys like Barton and Concealman or something who invented it. Yeah, that's right. Yeah. Yeah, but BNC, there's so many possibilities for those three letters,
Actually, I don't think that one would work. I see the bushing in there. That's 50 of them.
Oh, okay. I guess I grabbed the wrong picture. Thanks for pointing that out. I'll change that. Yeah. Good eye. One of the advantages of network connectivity is bidirectional signals and multiple signals at the same time. So this is our CCU, 12 connections to the CCU, kind of typical. This could be the CCU in the future. There's no reason, let me say that we use embryonics. Sony is using embryonics. Embryonics is kind of the de facto right now. It's good, but they haven't caught up with everything they need to do, so we can't do everything we want to do. Right now, we're just outputting ST2110, but in the future, there will be more and more capabilities. We started with ST2022. That was just SDI over a network. Very simple, straightforward. It was MPEG-2 compressed, and as you know, ST2110 is not compressed. It therefore required SDI to be de-embedded and things like the audio. And with ST2110, those are all separate signals. If you wanted to take just the audio feed with ST2022, you'd have to take the whole 1.5 or 3 gigabit signal, and that's sloppy. So 2110 does a much better job of that part of it. This is a close-up of it. Session description protocol, the text file, is critically important. It looks like a little bag on the side, but nothing happens if it's not in there. This tells the receiving equipment, if you're transmitting, what it is that I'm sending. Without that, nothing works. NEP was telling me they did a job at 1080i. The next week they had to do one at 720p. SDP had to be completely rebuilt. These are some of the problems that we have with the protocols with ST2110. Moving the data over a network is not the problem. I'll get to more of that. These are some of the benefits. The COTS equipment sounds like a good argument. I put possible future cost reductions. It's the EXE, isn't it, Bob? Yeah, what is it, $500,000 or something for a big one? Yeah, I mean, they're not cheap. I'm not sure where all this COTS low cost stuff is coming from, but it isn't coming from that router. Well, that switch, which we call a router. So I'm not so sure about the cost reduction in the short term. It's currently uncompressed. There is the compressed version in committee, and it uses a highly accurate synchronization called PTP, Precision Time Protocol, and it's based on existing standards, and all this flexibility, availability, scalability, infrastructure reduction, they're all good things. Nobody really argues about any of those. It may be a little ahead of its time right now, that's all. So this is the suite of standards, and the suffix talks about the specifics of that part of the standard. And, 211020 is the video, but without the system, the time stamps, the traffic shaping, nothing would work. Normal data networks are bursty. So there's a burst of data followed by a period of virtually no data. In video, it's a massive amount of data that does not stop and cannot stop. And so this traffic shaping is critically important to making it work. It doesn't appear to be important right at first, but it is. So these are the basic pieces that are used for delivery, multicast, one-to-many, real-time protocol, and UDP. Both are send it and forget it. Don't wait for an acknowledgement or anything. It goes, it's gone. It's kind of like broadcast. You send it out there and it's over. And they're using TCP/IP as the rest of the internet does. Here is PTP. You can see here that the active grandmaster feeds boundary clocks, which then connect to various pieces of equipment. You do not need a separate cable for sync. It's in there with the rest of it. And you can see how you can create legacy sync and blackburst from the PTP grandmaster clock. They're also GPS connected over great distances. You can keep them synchronized. A great way to get into this world is by using a switch that has ports that allow the SFPs to plug in. This particular one has one BNC in and one BNC out. Piece of cake. That's all it takes to get on a network. That could be an embryonics, it's not, but that's all there is to it. These are the groups that have worked together to put ST2110 together. And these standards groups include the IETF, which is the Internet Engineering Task Force. I believe I got that right. And these are standards of the internet that ST2110 sits on top of. And here's the problem. You've been waiting. AMWA and NMOS are not moving along particularly quickly. I know that there's a lot of frustrated people at SMPTE who would like to see a little more progress. It almost seems just a little bit like they want to keep it to themselves. You might be smiling, yeah. But we really, Bob said he has an Evertz and he's doing 2110. Great, Evertz works with Evertz, no problem. What happens when you connect the Evertz to a Ross or a Imagine or a whatever? Will it work? It's kind of a crapshoot whether it will actually work or not. And that's the problem. So, and that's my presentation. That was fast. Phew.